when you sell to Japan. It's natural, punk rock. Red, white, and blue.
All right, well, welcome to lecture 1.3. I don't have anybody in the room today, but I'm still going to go through the lecture so that everybody can benefit from the recording of it. Unfortunately, that means that I don't get any awesome student questions coming through, so oh, here comes Wes. So I've got one student in the room now, and Wes is really good about asking questions. So Wes, keep asking your questions like you always do, because I'm sure that all right, Michael and Wes, I see y'all are in the room. I'm sorry I lost connection there for a minute. Let me get my video going and we'll jump right in. All right, can y'all both see and hear me okay? Just give me a green check if you can. And Michael, you've got an icon next to your name that I'm not familiar with. It's a little screen. I don't think you're on a mobile phone. Oh, maybe it's a tablet device. Are you on a tablet device, Michael? Okay, great. All right, so new to me. I had not seen that icon before. All right, let me go ahead and clear these checks out here, and we will get going. It should not take me. I shouldn't be past 4. This is a shorter lecture, so I apologize for the delay here. Let's get going. Let's see. Let me get my page explorer reset here so I can move through the pages on my PowerPoint. Okay. All right, so hopefully the page changed for everybody and we're good to go. We're recording, yes. All right, so the first thing that you encounter in section 1.3 is the idea of increasing, decreasing, and constant functions. Now, this is a screenshot taken directly from your book, and the way they have it worded can be very confusing, which is what you have me for, to kind of translate this weird math language for you. So number 1 there says a function increasing on an open interval I for any x sub 1 and x sub 2. So those are just talking about 2 different x values along the x-axis. And it says there that x sub 1 is less than x sub 2, meaning that you can tell from the diagram, excuse me, my nose is itching, you can tell from the diagrams below that all that means is if you are traveling from the origin in the positive direction on the x-axis, that you'd hit x1 first and then x2. So it says if that is how you're set up to hit x1 and then x2, if your function is increasing, then f of x is going to be less than, f of x sub 1, so the y value of the first x point is going to be less than the y value of the second point. So, like I said, that's really confusing to think about. And it's just the opposite for decreasing. So here's a very much easier way to understand this. Let me get my pen going here. Let me get a different color than the blue. All right, so the first thing that I want to point out is that you read increasing or decreasing from left to right. So from left to right, just like you read a book in the United States, because not everybody reads from left to right. So if your function is increasing, if you're looking at it from left to right, it's going to do exactly what it says it is. It's going uphill. So a really simple way of putting increasing, uphill, left to right. Decreasing, just the opposite, downhill, left to right. And we also have constant functions, so neither. If we want to use our uphill, downhill lingo, this would be a plateau. I think that's how you spell plateau. If not, forgive me. Okay, so let me see if I can get this right for you guys to see. Here we go. Increasing, left to right, going uphill. Decreasing, constant. Now, here is the tricky thing that students have a little bit of issue wrapping their brain around. Most of you can look at the graph and say, okay, increasing, decreasing, neither. But you state it as it's happening through the domain, as it occurs across the x-axis. For example, let's take this first graph here that is increasing, and let me give some values to some actual values to the scale here. So we'll say that this function's domain starts at -5 and it goes uphill all the way to, I don't know, 13. If I were stating the increasing interval, so I'm just going to put INC for increasing, I would say this is increasing between -5 and 13. Now, let me point something else out. This interval would not be different even if the endpoints were colored in. That is because at the endpoints or at a place where it changes from increasing to decreasing, so at the top of a hill or the bottom of a valley, at those points, it's neither increasing nor decreasing. Those points just are. So I'm not going to use brackets ever. I will never use brackets when I'm talking about increasing, decreasing. You will always use parentheses with that, meaning up to but not including, which we learned in yesterday's lecture over 1.2 when we talked about interval notation. So, although the up and downness, the increasing and decreasing is happening vertically, so in the Y values in the range, you state it as it happens through the domain from here to here. So from here to here, it's doing this type of thing. Hopefully that's clear to y'all. Does that make some sense to you? Michael says yes. Wes says yes. Yay! I think that's one of the few times I haven't gotten 100 questions about increasing and decreasing so far. So that's what I have stated down here about how you state the interval. Open intervals describing whether functions increase, decrease, or are constant use x coordinates and not the y coordinates. You're stating as it happens through the domain. All right, let's move ahead. So we have some graphs here, and we are asked to state increasing, decreasing, constant. And you can have, obviously in that first graph, you can have multiple things happening in different intervals on the same graph. So here's how I set things up when I want to talk about increasing, decreasing, and constant. I give myself visual boundaries on my graph. So I'm going to give myself boundaries where the graph changes from increasing to decreasing. And the reason I want to do that is because I want to start focusing in on the X values where that change is occurring. So I've got my boundaries there for that first one. And I will just label, for the sake of the video, let's see, this is 1, 2, 3, 4. This right here is -5, an X value of -5. 1, 2, this is an X value of -2. Oh, I missed one. Let me go back and put that one on there. Can't forget this one. Different shade of yellow there. Okay, so my next boundary is at an X value of 0. And then I have 2, 3, 4, 5. Okay, so another thing that I do is I mark my graph using arrows to show which direction this thing is moving left to right. I know this sounds like a lot, but it really will help you see what's happening. So if I start at the left, I'm going down, downhill until I hit that boundary. I'm going to go ahead and mark all of my downhills. Here's another downhill and another downhill. So I'm just putting the arrows in the direction that it's going. And now I'm going to go back and mark my uphills. So this is uphill, uphill, and uphill. Okay. And I'll remind you, because this is going to come into play in this graph, out here is negative infinity if you keep on going in the X direction, and out here is positive infinity if you keep on going in the X direction there. All right, now we're ready to actually state the intervals. I'm going to keep this color-coded too. My decreasing intervals. So, I have decreasing intervals. Remember, I'm about to state through the domain the X values that this is occurring over. I am decreasing from negative infinity to -5, or I'm decreasing from -2 to 0, or I'm decreasing from 2, sorry, that's a parenthesis, 2 to 5. I have 3 decreasing intervals. My increasing intervals. I'm increasing from -5 to -2. I'm also increasing from 0 to 2. I'm also increasing from 5 to positive infinity. Notice all I've used are parentheses, up to but not including. Let me clear out the checks and the X's just to make sure. Are y'all okay so far with this? If you've got questions, ask them. I usually have 100 questions when I'm teaching this face-to-face. It can be tricky to see. Okay, excellent. Got a couple of smart men in the room here. All right. Let me give you a moment to try to do this next one by yourself, and then I'll do the last one with you because that's a little tricky. So go ahead and give that second one a try. I'll give us some background music to give you a moment to try it on your own. If you want to, you can type your increasing and decreasing intervals into the chat window. You don't have to, but if you want to give it a go, you can. I'm going to go ahead and start marking my graph. All right, I'm going to go ahead and write the answer out. Any questions about that one? Oh, we lost Wes, Michael. Michael, are you good with that one? Okay, great. Did you get it? Did you try it? I'm just kidding. You don't have to answer that. All right, so this last one, we actually have some funkiness here because it's a step function. We have three different constants. Because they're each constant, it's not increasing the whole time like the continuous increase that we have in these other two. Although it does look like it's stepping uphill, these are three constant intervals. So I am constant from -2 to 0, from 0 to 2, and from 2 to 4. Those step functions can be funky. You good? Michael, are you good with that? Okay, maybe you have a delay. I'm going to go ahead and move forward, but just raise your hand if you need for me to go back. It won't erase anything I've written on the screen here. All right, next slide. Okay, so after you talk about increasing and decreasing in this particular section, we move on to exploring the concept of relative maxima and relative minima. Relative means that there can be 3 or 4 maximum, I don't want to say maximums because the plural is maxima. You could have 3 or 4 on the graph, and so if you choose one, that's just considered a relative maxima if there's more than one on the graph. If you have a few maxima or minima on your graph, you can also have absolute maximum, singular, and absolute minimum. That would be the highest or the lowest point on the graph. So Relative maxima and minima, once again, your book gives this very confusing definition of it. All it is the peaks and the valleys, the high points and the low points on the graph. So bottom of the valley, top of the mountain. Those are your relative maxima and minima. So you can see that if some graph looks like this, you could have a few of each. So once again, maxima and minima is just the plural of maximum and minimum. The points at which the function changes its direction, so you're changing from increasing to decreasing, or blank behavior can be used to define. I wrote these notes about 1.5 years ago, and I have no idea what I meant to put in that blank. It's just where it changes from increasing to decreasing, decreasing to increasing. So if we look at this example here, I've got this curve running across my graph, and I have a low point here, which is a minimum, and a high point here, which is a maximum. And you can see, I mean, it can even be weird values like pi over 2. And when you get into 1113 trig, you're going to have weird values like that in your problem. So hopefully the idea of maximum and minimum is not some big revelation for you. It's just high and low points. And once again, we really talk about it in the sense of changing from increasing to decreasing, decreasing to increasing. Okay, so if I am, and by the way, let me continue this graph. This is coming up a little bit and then going off like that. So I'm just extending the graph there. Same graph really there. Here in this first graph, I have a maximum here, so this is a max. I have a minimum here and a minimum here. So I have 2 relative minima. This is a min and a min. Now, let me talk about the language that you're going to see MyMathLab use. You're going to be asked 2 questions usually about maxes and mins. You're going to ask where the max and the min occur, and you're going to be asked what the maximum and the minimum is. The where is asking about the x value, where that max and min occur. The what is going to be the y value, or the f of x value, where that max and min actually is. So, for A, it says the numbers, if any, at which f has a relative maximum. That's the where. So it's asking where on the x-axis are these maxima occurring. So in this first one, so for A, we're talking about maxes. The where in this first graph is at 0. X equals, here I'll write x equals, just so that it's confusing. The what? So what is the relative maximum? It's 4. So it's asking for the y value. That's that point right there. So it happened at an x value of 0, and it happened at 4. Hopefully that's clear. B is asking us to identify the minima. So we've got 2 here. The where, so the numbers, if any, at which f has a relative minimum. We have it at x equals -3 and 3. We've got 2 of them. The what? So what is the relative minima in both of them? It's 0. You good, Michael? Good. Great. Okay, so we'll go ahead and move on to the next two. I have, it's almost the same graph here, relative minima and a relative maximum, one of them. Okay, so A is asking about the max. Let me label this just for clarity's sake. So this is asking about maxes, and B is asking about minimums, mins. All right, so max for A. All right, so in this particular graph, we have one maximum. It is happening the where at x equals 0. What is the maximum? It's 2. The minimum? The minimum, the where? It's happening at -3 and 3. And the what is -1. Now this last one is slightly trickier because you have to remember what you learned in section 1.1 about viewing windows. So this down here, this notation here, tells us what kind of viewing window you're looking at. So remember, it always lists the x-axis first and then the y-axis second. The x-axis starts at -4, so this is -4, -1, -3, -2, -1, 0, 1, 2, 3, 4, because it's counting by ones. Now in the y direction, it counts from -15 to 25, counting by 5. -15, -10, -5, 0, 5, 10, 15, 20, 25. Okay? So you got to make sure that you can read those viewing windows. I have a maximum here and a minimum here. All right, so my max, the where, is at -2. The what is about 20, it looks like. Min, the where, is 1. The what looks like about -5. You ready for me to move on? Great. Okay, so I believe, yeah, this is the last big concept of this section. Sorry, I'm drinking my cold now, black coffee from 6:30 this morning. I'm getting a nice little caffeine jolt there. Okay, so even and odd functions. It is a common misconception among students that you can just look at an equation, for example, or a function equation, that you can just look at the degree and tell if it's even or odd. For example, if I looked at h of x equals x to the 5th plus 1, I'd say, oh, that's odd. That is not true. You have to run it through this process of determining the evenness or oddness of the function, because in actuality, number 3 there is neither. So let me talk about that for a moment. All right. Okay, so for even functions, and I'm just looking right up here at the definition. To determine if a function is even, or odd for that matter, what you want to do is plug in negative x wherever you see x in the function. So that's your first step, and you can see right here they mention the negative x going in, which is the very reason the last section had you practicing plugging those things in, because now you're using that knowledge here. All right, an even function is identified when you plug in negative x for x and it equals the same thing. In other words, none of your signs change. And I'm going to go through these at the bottom, so it'll be clear as mud. Now, an odd function, you start the same way. You plug in negative x, in for x into the function, but what you get out is negative f of x. In other words, all of your signs change. Then you have the option of neither. In other words, some signs change, some stay the same. So the function is considered neither even nor odd. All right, there are some characteristics that are associated with even and odd functions when you graph them in the xy plane. An even function is going to have what we call y-axis symmetry. So look at this first graph here. If I put a mirror on the y-axis here, you can see if that were, the y-axis actually does function as a mirror, and it's symmetrical on either side of the y-axis. Michael, are you still there? Can you hear me? Oh, I just got an email from you saying I can't hear you. Can you hear me now? Okay, great. I got a green check. Okay, it looks like it killed our slides. I'm so sorry. I think we must have, I know that it was flurrying here when I was coming back from lunch, so we must be having connection issues with the internet in general. So I'm glad you can hear me. I'll turn my video back on. Hopefully that won't kill us again in our room here. All right, I'm back. Thank you for being patient and not leaving. We're almost done. I was thinking that too. I was like, oh my gosh, we're almost done. Oh, my video stopped again. Okay, I'm going to turn my video off just because it might be sucking up bandwidth. Let me turn it off. Okay, can you hear me okay, Michael? Michael, can you hear me? Okay, great. Like I said, I don't know if you heard me say this, I'm gonna proceed without my video. I think it's sucking up precious bandwidth. Unfortunately, you don't get to see me in this. You just get to see a still shot of me. That was taken a couple of years ago in Puerto Vallarta, Mexico. Anyway, back to even and odd. What I was saying was, with an even function, you have y-axis symmetry. So it's like your y-axis is a mirror, creating symmetry. Odd functions have what we call origin symmetry. In other words, there is a mirror through the origin. Let me get my pen back here. Took my pen away. All right, so in this case, I could have either origin symmetry this way, or I could have it this way. So that is with odd functions. Let me just erase all of this off here. Then you can see with this last one here, you don't have y-axis symmetry or origin symmetry with that last one. And once again, that one is neither. So those are just visual characteristics of the graphs of functions with even and odd symmetry. All right, let me show you how you'd actually run negative x through to evaluate and see. All right, it kicks me out for another moment, but I'm back in here. Hopefully you can still hear me. Okay, so I am going to run each of these through the process of determining by evaluating to look for even or odd symmetry, or neither. Okay, so I'll take f of x equals x squared minus 6 first, and I'll do it right here. All right, so I start out with f of x equals x squared minus 6. Now I'm trying to determine if this thing has even or odd symmetry. So the process is to plug in negative x and see what happens with the signs. So this is negative x squared plus 6. All right, negative x squared, negative x times negative x is actually positive x squared plus 6. So notice, let me get another color so I can point this out. I have a positive x squared and I ended up with a positive x squared. I have a positive 6 and I ended up with a positive 6. Of my signs changed. That means, and you can also see from the y-axis symmetry here, this is an even function. When none of your signs change after you plug in negative x. Now let me do the same thing for the second example. So I'll do this here. I start out with f of x is equal to 7x cubed minus x. And to determine the even or oddness of it, I plug in negative x. 7 times negative x cubed minus negative x. So be careful whenever you plug something in, you always want to use parentheses because it does make a difference. Okay, so negative x cubed is negative x cubed. And negative x cubed times 7 is negative 7x cubed. Negative understood 1 times negative x is positive x. So let me point this out to you. You can see here, I started out with positive 7x cubed and I ended up with negative 7x cubed. I started out with negative x. In this case, all of my signs changed. So that means this is an odd function. And then the last one, if I plug in negative x wherever I see x, I'll do this one here. So I start out with h of x equals x to the 5th plus 1. If I do h of negative x, I get negative x to the 5th plus 1, which leaves me with negative x to the 5th plus 1. Okay? So, with this one, I had a positive x to the 5th here and a negative x to the 5th. However, I had a positive 1 and a positive 1. So in this case, some signs changed and didn't. This one is neither neither even nor odd. Green check or red X if you're good or not. Great. Thank you, Michael. And we've got one more slide. I appreciate you hanging with me even through the technical difficulties. Okay, so this is kind of putting everything together that we've talked about since 1.2, all with one graph. So hopefully this will really clarify any questions that you still had floating around. All right, so the domain of F, A. The domain is the span of the X values. Let me just point out that this thing keeps on going and it's slightly, very slightly inclined. So eventually, if you keep going, this thing is going to span the entire x-axis. So the domain of F is negative infinity to positive infinity. B, the range of F. And just raise your hand if you've got a question about any of this. Other than that, I'm just going to go straight through these because this is kind of wrapping everything up. But I'm happy to answer questions if you have them, Michael. All right, so the range of F. Now, since there are arrows on the end of this, it says it continues in this manner. It continues in this manner. So I can know that this particular function is never going to be above 4 in the y value. So it's always going to be below 4. So the range, and let me remind you, you state this in number line order from least to greatest. So the range of F is from negative infinity to positive 4 inclusive. Remember, we don't ever include infinity, so that's why I didn't use it on the domain or the first part of the range. But since we have an actual output value of 4 there in the range, I do include the 4. All right, let me clear off. Actually, I don't need to clear off our graph for these next couple. I can keep on with this same picture. Okay, x-intercepts. I have one here at negative 4 and one here at positive 4. So x-intercepts are negative 4 and 4. Those correspond to the points negative 4, 0 and 4, 0. I believe my math lab is okay with just writing the values and putting a comma between them if I'm not mistaken. Okay, you're only ever going to have one y-intercept if you're dealing with a function, and in this case, the y-intercept is 1. That corresponds to the point 0, 1. All right, coming into today's stuff, increasing and decreasing. The intervals on which f is increasing. So this thing is increasing, 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 increasing. Remember, it's stated as it's happening through the domain. Okay, so I've got another increasing, increasing, increasing. So my increasing intervals are from negative infinity, and this is the negative infinity I'm talking about. This one. So I'm increasing all the way from negative infinity up to negative 2. I switched directions there, Then I switch directions again at an x value of 0, and I increase again all the way to 3. Okay? I'm going to clear this graph so I can do decreasing so it doesn't get too confusing looking. Let me go get another color pen. We'll do green. All right, decreasing. Once again, here are my boundaries I have to work with. So I'm decreasing, 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 decreasing. So my decreasing intervals are between -2 and 0, and between 3 and positive infinity. So -2 to 0. Notice I never use brackets with increasing and decreasing. And then 3 to positive infinity. Okay, so the values of x for which f of x is less than 0. So this is saying for what values of x are your y values less than 0. Let me just draw the barrier that they're talking about. So they want to know for what x values does your function exist below 0. So that's this part of our function and this part of our function. I'm sorry, not just below, but also equal to 0. So it's less than or equal to. So we want to include those values on the x-axis there. Okay, so these are intervals, because remember this thing keeps going, going, going in both directions there. So the values of x for which f of x is less than 0, and here's the negative infinity I'm going to be talking about, and here's the positive infinity I'm going to be talking about, because you state this, it actually asks for the x values, and that would be from negative infinity up to and including -4, because remember we can be equal to 0 at -4. Or I could be equal to at +4 and less than all the way through positive infinity. The numbers at which f has a relative maximum. We actually have 2. Let me clean my graph off again. Michael, I really appreciate you hanging in here till the end. All right, so I have a relative maximum here and a relative maximum here. It wants to know the where, the numbers at which it has that relative maximum. So it's talking about the x values where they occur. So this is -2 and 3, and then the what? The relative maximum is, well, here it's 4, and here it's 2. And the last one, let me clean the graph off for this last one and get a new color. F of -2. So this says when I plug -2 into the function, what do I get out there? So if I run to -2 on the x-axis, that sends me up to +4. So f of -2 is 4. That is it. Let me go ahead and change to the last slide just to make sure everybody has this information. Your quiz will be opening tomorrow at 12 a.m. I'll be doing a quiz review tomorrow afternoon at 3 o'clock. So it'll be open all the way through this Sunday night, the 26th at 11:59 p.m. And I hope everybody can join us in the quiz review tomorrow to get any last-minute questions that you have answered. Michael, thanks again for hanging on through all the technical difficulties. If you don't have any questions, I'll just say have a wonderful day to you.